Hello friends, today we have to study the corollary of Hall's theorem. First we recall the statement of Hall's theorem. See statement. An XY bigraph G has matching that saturates X if and only if cardinality of neighbors of S greater or equal cardinality of S for all S subset of S. Here we see XY bigraph G has matching. Matching means first we see what is a matching. Okay, we take any graph. We take graph. This is a graph G. 1, 2, 3, 5, 6. 6 vertices. Okay, we want a matching of this graph G. Matching means we see definition. Matching means simply in matching no any adjacent edges. Okay, means the matching of this graph G. First we take this edge 1 to 2 edge, then second 2 to 3 edge not included, then 3 to 4 and 5 to 6. This is a matching. And what is a perfect matching? Perfect matching means degree of all vertices in the matching is 1, then it is called as perfect matching. We see another example. A, B, C, D. This is graph A. The matching of this graph is A to D, A, B, C, D. No any adjacent vertices. Okay, and this is a perfect matching because degree of all vertices is 1. We see another example. First we take this edge, then we can't draw any edge because these all are adjacent, and this is not perfect matching. Not perfect because the degree of 2 is 1. Okay, we understand the perfect matching. Now we see corollary of Hall's theorem. See statement. For k greater than 0, every k regular biparty graph has a perfect matching. K regular graph means degree of every vertices are same. If we see two regular graph means degree of every vertices is 2. This graph 1, 2, 3, degree of all vertices is 2. Also this graph degree of all vertices are 2. This is a 2 regular graph. Okay, and you know biparty graph, we have to prove every k regular biparty graph has a perfect matching. Okay, we see proof. First we take example of k regular biparty graph. Take any example. 1, 2, 3, 4, 5, 6, 7, 8. We take that example. This is a biparty graph. Okay, we see proof. We take name graph G. Let G be a k-regular xy bigraph counting the edges by endpoints in x and by endpoints in y. See example. We see this part is x and this part is y. Bigraph. These are bigraph. We count the edges of x. We count the edges of x 1 2 3 4 5 6 7 8 edges, and count the edges of y 1 2 3 4 6 5 6 edges, 8 edges. K into cardinality of x equal to k into cardinality of y implies cardinality of x is equal to cardinality of y. Hence it suffices to verify Hall's condition. A matching that saturates x will also saturate y and be a perfect matching. We take matching of this graph. One, two. These two vertices are included. Other two vertices. And last two vertices. 7 to 8. This is a perfect matching. What he say? A matching that saturates x will also saturate y. Here this part x, this part y. The degree of all vertices of x is 1. Also the degree of all vertices of y is 1. Now, second part. Consider S subset of x. We take subset of x. We take these three vertices. Yes, this is S. Okay. Let M be the number of edges from S to neighbor of S. You see in example, S to neighbor of S. Neighbor of S is this. Okay, because from the set S we take edges. This is the neighbor set, neighbor of S. Yeah, S to neighbor of S. This is given. Since G is k regular, M equal to k into cardinality of S. We given M equal to k into cardinality of S. Here cardinality of S equal to 1 2 3. Cardinality का 3, and k means 2 regular. 2 into 3 equal to 6. Okay, these M edges are incident to neighbor of S. These k edges incident on neighbor of S. Okay, so M is less equal k into cardinality of neighbor of S. Hence k into cardinality of S less equal k into cardinality of neighbor of S, which yields cardinality of neighbor of S greater equal cardinality of S when k equal greater than 0. Here we choose M equal to k into normalize cardinality of S. We put the value of M here and we get this. Okay,